Started.
All right, hello everyone. So today we'll be talking about three-dimensional rotation and the problems that occur, mainly gimbal lock. So last time I talked about rotation in 2 dimensions with complex numbers, and this won't include complex numbers at all. This will be purely just understanding the idea of 3-dimensional rotations to introduce the idea of quaternions for a future lecture. All right, so when we describe our rotation with mainly aircraft, spacecraft, submarines, we use what's called our yaw, pitch, and roll axes, and certain angles around these axes to determine our total movement and our total orientation. All right, next. And now we have something that really is important to the idea of 3D rotation. So this is called a gyroscope or a gyroscope. And basically what it does is the inner gimbal, the inner rotor, will spin really fast. And essentially it's able to maintain its orientation due to the conservation of angular momentum. And so if you had an adjustable mount on the bottom of, if you had this and this were able to adjust, and you were to rotate this, this would actually maintain its orientation in space no matter how you rotate it. Now, if you were to grab the whole thing and just twist it, then obviously now that you've applied some force to this object, then it's gonna, then it's gonna lose its the way it's rotating. But the cool thing about this is that it's actually used in a lot of different systems, and namely the inertial navigation system or the inertial measurement units. So the inertial measurement unit is something that's used in submarines, in spacecraft, and aircraft to determine both our acceleration and different factors. But the most important part that's very relevant to this lecture today is what's called the gyroscope part of the inertial measurement unit, which essentially determines the rotation. So here, you can see these 3 rings around this. We have one here, and then we have a middle, oh that's really bright, a middle rod here. And so the way that these 3 rods rotate basically determine the orientation of whatever is inside. And so the orientation and the way they rotate is actually determined by a computer, and so it's operated by a computer system. Yeah. All right, so now that I've introduced the idea of of the inertial navigation system and gyroscopes, to kind of understand what's really happening, we have to look back at the idea of a vector. And so a vector is basically a combination of the description of both direction and magnitude, which looks essentially like this. And so what we have is essentially what looks like an arrow, and this arrow describes in what direction we're facing, but also the length of the arrow, or the magnitude, describes how much of something is applied. And so we can actually describe any vector in 3D space using our 3 component vectors that are way up here. So we have 3 component vectors that sit along our 3 axes in 3-dimensional space that actually we can sum them up in different ways, and we can describe any single vector using that. So that's the idea of the vector here. Is you won't see the application just yet, but I'll explain what we can really do with these things. So all right, next. So okay. So now let's say we wanted to transform these vectors somehow, right? What if we wanted to, and I'm restricting our view to 2-dimensional space just for simplicity, and then I'll go on to the idea of vectors in 3 dimensions. But basically what we can do, what if we wanted to like transform our vector in some way? So whether that's a rotation or a stretch or a compression or anything in between or any combination of those, what if I wanted to describe a transformation of those vectors? So for example, we have our picture of Barack Obama here, right? And this picture of Barack Obama is bounded by these 2 vectors, I and j. And these 2 vectors are actually component vectors, 1, 0, and 0, 1. And now let's say we wanted to describe so in this example, we want to describe a rotation and a stretch of Barack Obama's picture. So here, what we've done essentially is we've rotated this, a certain number of degrees counterclockwise, and then we've stretched the entire image. And so we can actually use what's called the matrix to essentially describe what we just did here. And what the matrix does is all it is some set of numbers, some set of instructions that tells us how to move these two vectors to these two vectors. And if we're given just this piece of information, we can determine the outcome of anything on the two-dimensional space. And the same thing applies with 3 dimensions. So does anyone have any questions? All right. So basically what the matrix is it's a set of instructions that essentially tells us where we want our vectors to land. But the most important type of matrix that I'm going to be talking about today is called the rotation matrix, which only describes rotation. So no stretching, no squishing, just rotations about some axis. So, yeah. Okay. Now I have to talk about something kind of different. So rotations in 3 dimensions can be described. For example, if I want to take this calculator here, I have basically 3 ways I can rotate it. I have 3 different axes around I can rotate. I can rotate it this way, I can rotate it this way, and then I can rotate it this way, right? Those are our 3 basically unit rotations. And so the way we describe our 3 unit rotations are with angles around our 3 axes, x, y, and z. And so in this case, they have phi, theta, and psi. In the next example, I'll be using different angles. But basically what this does is it essentially tells us, it gives us a set of instructions. Okay, I want to rotate, phi number of degrees around the z-axis. I want to rotate theta number of degrees around the x-axis, and I want to rotate psi number of degrees around the y-axis. So that basically what we can do is we can describe any rotation, any like arbitrary rotation of my calculator, for example, as a combination of rotations about our 3 axes. All right. And so here, these 3 sets, I won't exactly explain. These are the matrices explaining the instructions to rotate, but here's what is really, really important up here. So we have our rotations about our 3 axes. So let's start with gamma. So gamma basically determines the angle. Gamma is the angle of which we rotate around the x-axis. So when we say we rotate around the x-axis just remains fixed in place, and everything else is rotating about it. So we have this angle. And then we want to combine it with some rotation about the y-axis. It does the same thing, where our y-axis remains fixed in place, and our x and z-axis are moving. And the same thing here. So now what we've essentially, and with same thing with gamma, but now gamma describes the rotation around the z-axis. So does anyone have any questions? All right. So yeah, and what these 3 boxes are, these are called matrices. I'm not going to explain exactly why we have gamma, beta, alpha, but basically this gives us a set of instructions to move around to move gamma number of degrees. This gives us the set of instructions to move beta degrees, and this gives us the set of instructions to move alpha degrees. So basically what this is it's a handy way of shrinking down our information to just a few pieces of information to determine some transformation.
Can you explain how to interpret matrices, since I haven't learned that yet?
Yeah. So the interpretation of matrices is not actually. So yeah, I'll explain it. I'll explain it a lot more in depth in my linear algebra videos later. But basically, this one. So basically, what this says is we have 3 vectors along the x, y, and z axes. These are 3 component vectors that have coordinates 1, 0, 0, 0, 1, 0, and 0, 0, 1. And those are 3 vectors. Now, if we rotate about the x-axis, the x vector remains fixed in place. And so the columns of this matrix are basically saying where our vectors go. So this one should remain in place. This one doesn't move at all, because this is just the x vector, and it's rotating about x. Now this one, cosine and sine, right, are just basically what we're doing with the angles is we're just moving x cosine degrees, y sine degrees. So the actual idea behind the matrix is it's a little bit more complicated, but basically the rows of these matrices, I'm sorry, the columns, tell us where our vectors are lying. And so that basically gives us the instructions to tell us where to rotate. Does anyone else have any questions?
Okay, thanks.
All right. And then, yeah, this is the last slide. Yeah, okay. So this is the kind of final slide. This is, so this is where we actually have some problems, right? So the idea that we can sum up just rotations with arbitrary angles around our axes is actually, it actually causes some major problems. And this is called gimbal lock. So what gimbal lock is it's essentially the alignment of two gimbals or axes together. And then we've just, what happens is if you compute it out, we've basically lost a degree of freedom and we've lost one way to rotate. So if we take a look at this example here, and the math correlates with this example, but this example here basically tells us, so we have our x-axis, y-axis, and z-axis here. And what's happening between here and here is